Recording in progress.
Hello. Let's see. Hi guys, can you guys hear me? Please give, let me know if you can hear me or give me thumbs up so that I know it's working well. Ryan, Jacob, and Elvis. Okay. Yeah, I saw you type yes. It's great. Thank you. I'll wait for probably another minute or so. Yeah, okay. Turn my video on so you guys can see me. Oops. Button. I'll give it one more minute before we start. So today is our really last lecture for the new contents. Yeah. So let me. Okay, great. Let's get started. As I mentioned earlier, today's lecture is our last lecture for new contents, and on Monday I will do a thorough review plus a quiz, and then on Wednesday next week we'll do our office hours, and on Friday we'll have our final exam. I want to mention to all of you that the course survey is available. So if you guys received the email with a link to survey the class, please do so. Your feedback is going to help me and also the department to improve future offering of this class. Anything good about it, let me know, and anything that you feel that needs improvement, also let me know. You can also email me, whether before the exam, or if you want something you want to say after the final exam, you want to email me as well. You're welcome to do so. The survey has to be done by Wednesday. So with that, let's continue with what we had last week. We were talking about the two-stage op-amp. This is a very typical op-amp with a two-stage. As we mentioned, there's no output stage, which we just talked about last week, how to build a output stage with class A, B, C, D our class AB amplifiers for the last stage. So if you do that, this will come up like this. So the last stage will be here. And also, you see here, the first stage is a differential amplifier, and the last stage is common source amplifier. And we do have current sources that are built in by Q8, Q5, and Q7. Those are current mirrors. And you also have Q3 and Q4 that is formed as a cascade or current mirror load for the device, for the overall system. Now, we already went through to talk about the input range, common mode input range. We also look at the output range. We look at the DC gain, and we look at input resistance and output resistance from our last lecture. In today's lecture, we're going to talk about the frequency response. Now, with last week, we also mentioned about CC in the circuit, and I said we're going to talk about this later, which is exactly what we do now. If you look at the CC, that looked like a feedback. So this CC looked like a feedback. I mean, this feedback, however, we're going to see the function today, but the feedback basically makes the system more stable and will help expand the high frequency response region. So that's what really we have. Now, in order to look at the frequency response, as you know earlier from the small signal model, basically, if you look at, let's take the last stage as example. We're going to look at Q6 as example, how to do the high frequency response. Well, we know that from the input, you have VGS1 coming in. In this case, this is equal to VO1. We can always draw both stages, but we're going to just use this one as example to make it easy for us to understand. So this is the small signal in the middle range, and when we want to do the frequency response for the high frequency range, this circuit does not impact really low frequency, so we basically are skipping that part, but we can certainly do that. Low frequency response. When you have a low frequency response, usually there are capacitors, things like that, put in the circuit. But in this case, we don't have any capacitors at the input for the DC busing, things like that. So we're not really worried about low frequency response. So we're mostly focused on the high frequency response. So for the high frequency response, we're going to add the internal capacitance of the circuit. Like in here, you have VGS6, and over here you have DG6, and there are also other resistance, if you remember, including VS, from also gate to from drain to source. Basically, there's something over here as well. But this resistance typically, no, I'm sorry. I used the wrong symbol here. It should be C. This is CGD, and this is CGS, and this is CDS. Now, the CDS typically is neglected because CDS is much less than CL, which this is like kind of the output capacitance. So therefore, CDS is typically neglected in the analysis. So this is the output stage. I mean, this is the second stage. So if you look at the first stage, between first stage and the second stage, you also have this capacitance of CC. This is where the CC comes in, and then from here we can draw the first stage. But from the previous chapters, we know that for the resistance of the first stage and second stage, basically we can use a simple equivalent circuit. This is what we're going to show on the next slide. Is for the first stage, we'll simply use C1 to represent all the capacitance of the MOSFETs. And we're going to use C2 to represent all the capacitance of the second stage, which is going to include the capacitance of Q6 and Q7. So this is really Q6 and Q7. And this one will be Q1, Q2. Also, you have the Q3 and Q4 other load. Everything has an internal capacitance. And CC is in between stage 1 and stage 2, forms like a little feedback. And we're going to, again, see more of this function later. For this equivalent circuit, what we did not include was CL, which we can include later because CL does not necessarily to be there all the time. It can be there, it depends. So we're going to look at the circuit with and without CL later on. So initial step, we're going to look at without CL. So that's what we're going to do. Now for the circuit over here, you probably already noticed this is a fairly simple circuit. Now, by the way, I need to clarify that GM1 and GM2. So what they did in the book, not to simplify the analysis, they said that capital GM1 is equal to lowercase GM1 and also lowercase GM2 when they are symmetrical. And GM2, the capital case GM2 is second stage, is equal to the lowercase of GM6. It's a little bit confusing, but we translated the lowercase GM, which is transconductance, to the capital case, which is kind of the gain of the transconductance gain of the stage 1 and stage 2. So in this circuit, if we do some mathematics of the equivalent circuit that we did before, we can easily find out that really C1 is just pretty much the combination of all capacitance of Q of Q2 and Q4, so here we're going to have C1 equal to CGD2 plus CDB2 plus CGD4 plus CGDB4 and plus CGS6, which is, now remember, this is the capacitance of the second stage input capacitance, which has nothing to do with CC, okay? And then we have C2, which is the second stage, that is equal to CDB6, which is the drain to base capacitance, plus CDB7, which is drain to the body, I'm sorry, plus CGD7, and then plus CL. So CL, earlier I mentioned that it's really here. Okay, so CL includes CL. So CC includes CL. So we have two resistors. Now, once we have these two resistors, two capacitors, we have these two capacitors identified. This circuit becomes very simple because we have one node here and another node here. So we can do a simple node analysis. If we do node analysis, basically we can, initially we don't have to worry about this because it's not even connect to the circuit. The only relation is GM1 times VID here. And also we have VI2, which is connected to the second stage. So let me draw the circuit here again so that we have a better understanding why I draw the equivalent circuit. So this is this is a GM1 times VID. And then we have, let's see, so we have R1. And then we have C1, then we have CC, and then we have This is GM2, which is capital, which is equal to GM6 times Vx. What they call VO1 or VI2, they call VI2, okay? So we can call this VI2. And this is CC, and this is R2, and this is C2, and this is your VL. So remember, we have already in the previous lecture, we found R1 is equal to RO2 and RO4, and R2 equal to RO6 in parallel with RO7. So those are given. Now, we also have C1 and C2, which is defined in this page here. So I'm not going to rewrite it. The key here is to write the nodal equations here. So we write the nodal equation at 1, because D1 and D6, which is the gate of the drain of 6 and the drain of 1, 2. So from D1, we can see there's how many currents going out? There are 4 currents coming out. So we can have GM1 times VID, which is 1 current, plus, let's call this so this is VI2, right? So because here from the capacitance that we have VI2, so it's VI2 divided by R1, and then plus VI2 plus the current in C1, which is SC1 times VI2, and then plus the current in CC, which is SCC plus times, this is going to be VI2 minus VO. And the whole together is equal to 0. So this is D1. At D2, we have also 4 currents. And you can see there are 4 currents. But this right now, there's no load resistance. So the current over here is 0. Okay. So then we have GM2 times VI2, that's 1 current, plus VO over R2 plus SC2 VO. And then we also plus SCC is VO minus VI2. So from here, we have 2 variables basically. So VI2 and VO. So we can solve the circuit for VI2 and VO. And eventually you will get a function of VO. We will get a function of VO as a function of like VID, which is input. And if you get this ratio, and then you have this gain, which is basically as a function S is VO over VID. Now, how much is this one? Because of the capacitance involved, this becomes a little bit complex. And these equations, of course, are given in the book. But what I'm going to do is I'm going to write a simple equation. And we know that if you look at it here, we really have 2 capacitors, 3 capacitors. And if you remember in the previous chapter, the CC between these 2 can be actually break down through the using the Miller equivalent circuit. But here we could do it, but here we don't have to do it. We just simply going to derive the relations. And what we found is this AS is going to be a function of VO over VID. And this is going to be a very complex equation, but I'm going to write this way so that you understand better. So it's going to be a function of GM1 and a function of GM2 minus SCC times R1, R2 as a denominator, and as a numerator, and the denominator has a form of a plus 1 as plus b s squared. And here, the A is quite complex. And I can write down like A is equal to C1 times R1 plus C2 times R2 plus CC times GM2, this GM2 times R1, R2 plus R1 plus R2. So you can see that this is quite a complex equation. I write down, but you don't have to remember this because this can be mathematically derived. And in fact, a lot of the design work is done not by hand, by computers, by like Simulink, by LTSPI, so this equations automatically. A lot of time you don't see them, but for the to understand the principle, it's good to write them down so that we have a better understanding of the circuit. So this is equal to R1 times R2, and then times C1 times C2 plus CC times C1 plus C2. So B is a little simpler. Now, with that, what we're going to do is we find that this gain for the high frequency response, we have 1, 0 at the numerator. So basically, if you let GM2 minus SCC equal to 0, you got that 0, which you have this like SZ equal to GM2 divided by CC. And you know that this is, if you look at here, where is that in a complex plane? In the complex plane, where is that 0 located? Well, we know that 0 is located in the real X, which is here. So this SZ. So this is called the left plane of the complex. And this contributes, if you look at this one here, this contributes what we call a 90-degree phase shift for the overall circuit. Okay, so this is one of the zeros. We only have 1 0. But for the denominator, because it's A plus AS plus B squared, we do have 2 poles. So 2 poles. So for the 2 poles, how do we get the 2 poles? You probably already remember, in order to get the 2 pole, we need to get, we can have this to 0 to solve for S, and then you can have S pole 1, and you can solve for S pole 2. But because A and B is a little bit complex, so in theory, we can do S equal to minus B plus minus B squared minus 4A for B. Well, you know what? I'm going to change my convention. I'm sorry, because this makes it a little bit easier if I do this way. Instead of this, let me do this. I'm going to do this. I'm going to call this B. So I'm going to do, just change the convention to here. So this is, let me call this B, then they call this C. In this way, we have a quadratic equation. Now this C is not capacitance, it's the quadratic equation. So here we will have B, C, and then this again will be 4AC, which A is 1 and times 2A. So in theory, you can do this one to get S1 and S2, right? But for simplicity, what we're going to do is we're going to do it in a different way. So what we're doing is we're going to let ds equal to 1 plus, now I'm going to call B S plus C S squared. Now this C is a constant. Now, this C is not a capacitor, okay? Just don't confuse. Not a capacitor. So what I'll do is I'll let this one equal to 1 plus S over omega P1, 1 plus S over omega P2. So this way we can extend this one. So we know that these two are going to be equal. So we extend TS, we'll get S times S plus WP1 plus S over WP2 plus S squared over WP1, WP2. So we get this one. Now this can be further written as S WP1 plus WP2. I'll explain to you why we do this, because this will make the calculation much easier. So in this way, you can see if I have this one to compare with this equation here, you would get B equal to 1 over WP1 plus 1 over WP2. And you will get C equal to 1 over WP1, WP2. So if you look at the previous page, we have C equal to this value here. So, and what we also know, now this will need some kind of experience to know what happened. But if you actually plug in the numbers, you will find that WP2 is significantly larger than WP1. So so WP1, which means WP1 is significantly less than WP2. So if this happens, what it means is that 1 over WP1 is much larger than WP2 over 1. So now you look at what happens here. If your WP1, 1 over WP1 is much larger than WP2, what you really get is B is simply equal to 1 over WP1. So that's our conclusion is WP1 is simply equal to 1 over B. And the B, we already have this value here. We already derived in the previous slide. So what we can write is here, okay, so we're going to write this one to CR1 plus CR2, and then plus C times C CC times GM1 GM2 times R1 R2 plus R1 plus R2. So we write this from B a little bit, and we got this. And the reason we write this way is because R1 and R2 are much smaller than GM2 times R1 and R2. Why? Because you know that R1 is in the kilo ohms and R2 is in kilo ohms. So if you use, let's say 10 kilo ohm times 10 kilo ohm, it's going to be 10,000 times 10 kilo ohm. So basically, what you're saying is that R1 times R2 is going to be 10,000 times larger than R1. So therefore, in the circuit over here, we can simply neglect that, and this is C here, and you can neglect this too. So, so these two terms, which means C1 and R1 and C2 R2, are also much smaller than CC. So what you write is omega P1 equal to 1 over C1 and R1 plus C2 R2 plus CC GM2 times R1 times R2, because that R1 and R2, this basically we neglect this one because it's too small. And now we see that CR1 and CR2 is much smaller than this value. So therefore, you can further simplify this into CC times GM2 times R1 times R2. So you can, so this is your WP1. Then, so what we did is by some simplification, we get WP1. Now this simplification process is based on the principle, which one is bigger and which one is small. Because, I mean, apparently CC times GM2 times R1 times R2 is much larger than R1 times C1 or R2 times C2. So we get WP1. So now we go back to here. We see here WP2 here. So we have WP2 equal to 1 over WP1 times C. So we have, now we can write WP2 equal to, really that number is going to be it's going to be if you have any doubt, you can always go back and cross check. It's going to be 1 over WP1 times that C. Again, this C is a constant. And by plugging WP1 and C into this function, we get, which is equal to GM2 times CC over C1 times C2 plus CC times C1 plus C2. So again, you will see that this WP2 is much larger than WP1, which, well, we can rewrite WP1 here. So WP1 is equal to 1 over GM2 times CC times R1 and R2. The reason is R1 times R2 is very large, right? So therefore, WP1 is small. And this fairly, I mean, by this time you already see, well, WP1 and WP2, they do exist, but WP1 is much larger than, and WP1 is much larger, WP2 is much larger than WP1. And in fact, we can further simplify WP2 because CC1 with WP2 can be further simplified. The reason is C1 plus C2 is going to be much smaller than CC. So which means this one, you can simply neglect it. If you neglect it, you'll find that this equation becomes no, sorry, this not this one. Is C1 plus C2. C1, this one is going to be neglected because C1, C2, normally the capacitors C1, C2 much smaller than CC. So what I read down is, should be right down here. Instead of writing that way, we're going to write down. So C1 is much smaller than CC, and C2 also much smaller than CC. So therefore, here we get that neglected. And then we get this equation here, WP2 equal to GM2 over GM2 over C1 is much smaller, C1 much smaller than C2. Oh, in fact, no. Let me write down here too. So C1 is much smaller than C2 because C2, okay, because C2 has CL in it. CL is much larger typically. So this way we can have so this one is going to be, so we're going to neglect C1 is much like, so we're going to neglect this one here. So we're going to like this one here. So GM2, C1, C2 times C2, and then this is CC. And over here, we can have, again, further neglect, we're going to get GM2 times divided by C2. So we further neglect this one, and then this one cancel. So we get GM2 over C2. So this is the final expression for the pole, for the second pole, WP2. If we draw the complex plane, and we already know that there's 1, 0, which is WZ over here. And then we have WP2, we have 2 poles. We have 2 poles. So one is here, one is here. So this is WP1 and this WP2. So at this point, we can further write the expression of that Frankfurt response. Remember the Frankfurt response that we get was AS equal to, I just want to go back to you guys here. So which is this one here? And also we have the equation of SO here. Now we're gonna plug in this one. We're gonna get this equation over here. So this is gonna be, write this down. GM1 GM2 minus SCC times R1 times R2. And this one pole over here, and then at the numerator, we have 1 plus S over WP1 times 1 plus S over WP2. So we have 1, 0, and 2 poles for the transfer function. Now with this transfer function, what we can conclude is that the WP2, as we know that, is much larger than WP1. And in fact, the 0, which what we got from earlier is the W0 equal to GM2 over CC, has also going to be larger than WP1, much larger than WP1. So in other words, that if you want this WZ to be larger than WP1 and then WP2 or larger than WP1, we can bring the equation back from our previous slide. Is what we have this WP1 equal to the final expression, WP1 equal to R1 times CC times GM2, which is the second stage gain, times R2. That's WP1. Has to be much smaller than WP2. And the WP2, the equation was GM1 divided by CC. Again, this is the final approximation. This is WP2. So this is one equation. So by combining this equation, you can see that you can find out what the relation between GM1 and GM2 and so on. So from the second one here, we can say WZ is WZ is equal to GM2 over CC, has to be much larger than WP1, which again is also R1 C GM2 R2 over 1. So by using these two equations, and we can find some useful values for us. The other thing that I just want to mention is that you remember in the previous lectures, we talked about the unit gain. I don't know if you still remember this unit gain stuff, unit gain. What this unit gain, I want to bring this up because this is very important to understand. Because we need to understand what happens with the stability of the system. If you remember, what we did was, if you have any transfer function, AS, and in our case, it's going to be some sort of gain, which at the middle band times you have S minus W0, and then you have 1 plus S over WP1, and 1 plus S over WP2. And that's kind of your transfer function. And if you look at here, from here, we can also get A0. We remember we got the middle band gain already last lecture. So basically, when S is approaches infinity, or S approaches small, not infinity. S per infinity gives you the large high frequency response. But in this case, when S is small, and when S is small means this can be neglected, this can be neglected, this can be neglected. So you get this gain to be GM1, GM2 times R1 times R2. So this is exactly what we got for the middle band gain, right? So you have this, by plugging this GM, so GM2 1 plus, so it's going to be 1 minus here. Make it really make this clear. So this can be 1 minus S over WZ. Okay. So remember, we can always replace this S with the J omega. So therefore, we can get this gain to be A0 times with absolute value if it's negative, but in this case, it's positive, we know it. And then plus this actual, in this case, for example, it becomes 1 plus omega over WT squared. And then at the bottom, you have 1 plus omega WP1. And then you have 1 plus omega WP2. This is we're going to just get the actual value when frequency changes. And then also there's an angle. So we get that angle. So the angle that you can see, the top is really 90 degrees. And then so we have really just this A0 times the huge number over here, and then times angle phi over here. So I'm going to write down this value. So as you can see here, if we let the whole thing here equal to 1, and that's called a unit gain. So 1 omega increases, let me further write down here. So 1 omega is small. 1 omega is small, which is low frequency. It's in the middle band. And A S or 1 J omega equal to A0. When S omega increase, it becomes high frequency, and we get the gain A is going to decrease. Why is it decrease? Because you got omega at the numerator, but 2 omegas at the denominator. So what omega over W T, but omega Z, or omega over WP1, omega P2, they're much less than 1, because when omega increases, and this becomes much larger than 1. So each of this value is going to be, at some point, it's going to be much larger than . So if they're much larger than 1, if you look at the top of the page, what we have, if we can neglect that 1. So now we have this 1 A J omega equal to A0 times your bottom has omega, or omega T, or omega Z, your bottom has omega over omega p1 times omega p2. And then you also have an angle. The one omega is going to cancel. You have another omega. So this equation becomes A naught times 1 omega. You have 1 omega, then you have WP1, WP2 over WZ divided by omega, and then times phi. So your gain will actually decrease as omega. So 1 omega increase, your A would decrease. So when your A decrease is what will happen. So this, now we can draw the gain as a function of omega. So we know that in the middle band, we have this at A0, it's middle band. At some point, this is gonna decrease, okay? And decrease, this is your W0, your P1. And then at some point, we have our WP2. So this is our WP2. And so this is dropped by 20 dB per decade. And this is going to drop minus 40 dB per decade. And at some point here, we got our W0, and this further drops like this. And at this point here is what we call a middle band gain. And of course, this WP1, it cannot be, in fact, it should not be at the above. If it's above, the system is unstable. So the ideal drawing will look like, in fact, it look like this. So this 20 dB drawing, and then we have 40 dB, and then we have 20 dB. So here is our WP1, this W0, and this our WP2. That's our body plot. Now, in the same plot, we can also draw phi. And our phi equal to, if you look at here, we have 1, 0, and 2 poles. So our phi can be written as the degrees of your or your 90 degree, basically plus your tangent minus 1 and F T over F P2 plus tangent minus 1 F T over Fz. So the first pole basically give you a 90 degree shift. So this is your 0. So you initially there's no phase shift. So by sometime like here, you already got 90 degree phase shift. Okay, and then by this point, you have here, you have another phase shift, and then you have another phase shift. So there. So here is where we have this 100. You remember we talked about the phase margin and the gain margin. So if this is a unit gain, this is a unit gain. Unit gain means 0 dB. Unit gain. Unit gain means A S is equal to 1 and dB is equal to 0, right? So that's unit gain. So at unit gain, this cannot be 180 degrees. This has to be of here, from here to here, we call it phase margin. And at 100 degree, here, the difference over here, we call gain margin. So this gain margin and phase margin has to have a certain value, otherwise the system will not be stable. So this is kind of our body part drawing. So one of the interesting things that we see at high frequency is if we go back to, again, the gain here, if you look at the gain here, what happens is when the frequency is high enough, when the frequency is high enough, you really get, this is inversely proportional to omega. The gain is inversely proportional to omega, and there's a phase angle. So what we can do is we can go back to the equation that we had. Let me see if I get this correct. We can have this equivalent circuit where we can draw the. Give me 1 second. I'm gonna find out. Yeah. So if you look at the really the high frequency response of the circuit that we have, it's going to be really interesting because it becomes simply just a integrator over the region that we wanted. Just I misplaced one of my pages. Yeah, here. Oh. So our circuit gain becomes A equal to, so let's call it AS equal to GM1 times VID. That's your input times, or in here, or we can actually write the voltage from here. So this is VO, this is 0 volts. And this, again, I'll let you know how we derive the circuit over here. Because the current does not, so there's zero current going in. So all the current here will go to VC. So basically you have VO minus 0 equal to the voltage drop on SCC is GM1 times VID divided by SCC. So in other words, remember the current of a capacitor equal to C dV over dt, right? Or equal to SC times V. That's what we have in a capacitor. So therefore, in this case, we have VO equal to GM2 times VID divided by SCC. And we got this equation because if you remember from the previous slide, let me see which equation we have, is where we have this W at very high frequency, at very high frequency, where OAS equal to simply the pole, the first pole can be neglected, and the second pole, which plays a main picture here, is what we got is CC. Yeah. So we have our gain eventually equal to GM1 MID divided by here is the equation here. At a high frequency, it becomes GM2. I need to go back to this equation here. Yeah, here. So GM1 times GM2 times R1, R2, and over, we neglect one. So this pole can be neglected, and then this pole here. So basically, we neglect this one, and we neglect one pole. So we got S over GM2 over S times CC. So from the previous slide, we can derive this one. And this means VO equal to GM2 times VID divided by SCC. That's our really upper voltage. So what this does is that it's like an integration. So what it tells you is that in a certain in a certain range, this becomes integrator. So if your input VID, let's say is VID maximum times sine omega t, so your output VO will become GM2 times VID, which is VID hat times cosine omega t divided by omega, and then this there's probably so it's VO is the integration of VID, and so this is how you really get your output, which here is minus sign. So its integration means if your input is sine wave, your output will be a cosine wave delayed by 90 degrees. So it's like this, by shifted by 90 degrees. That's your output. This is a very interesting phenomenon because what you're saying, your two-stage amplifier at high frequency, it looks like integration from the first stage output. The input is here, times VGM, times GM1 is your output of your first stage, and it fits in the second stage, but the second stage becomes like integrator and with infinity gain. This is a very interesting phenomenon because the gain of the second stage doesn't make any difference anymore because it looks as an integration. It's just like an integration of your input to the first stage. So we already draw the equivalent the body plot, and I already show you that this is your middle band gain. Middle band gain, as we know that this is equal to like 20 log. Where this you have GM1 times GM2 times R1 times R2. So this is what S is small. S is small. Okay. So you have the middle band gain, which is given, and here is the dominant pole, which is FP1, right over here. So FP1 is a dominant pole. Introduce a minus 20 dB drop per decade, and over F between FP2 and FZ, so FP2 induce another minus 20, so it becomes minus 40 dB per decade drop. By after FZ, it corrected, so it becomes again 20 dB per decade drawing. And the phase margin is calculated one at unit gain, and to see between how long is you between 180 degree, that's your phase margin, and between the 180 degree to here, and here it gives you your gain margin. So this is your and this is very important because this two-stage amplifier can become unstable at some point. It's primarily because the phase shift caused by the initial 90 degree here caused by FP1. So if our transistor operates like right below this frequency, there's no issue. But between this frequency and above, we have issue. Also, when we use this in feedback, we might have issue as well. So the idea in the book, what it tells you, we can introduce a resistance with CC in series with CC. And this is an elegant concept because by introducing R, the actual gain, the pole, if you remember the equation that we had for the zero, is it becomes really just S equal to 1 over CC times 1 minus GM2. We're going to neglect all the steps to derive this. Instead, we just simply analyze result. So it introduced this zero by this little change in the bottom. you see here, we have this R introduced. So if you select the value of R, you can select R equal to 1 over GM2. You see what happens? S approaches infinity, which means your W0 is infinity. And this infinity means, if we go back to slide, means this 0 will be infinity, so this line will actually drop like if indefinitely at 40 dB. It will never go back to that 20 dB anymore with a finger correction. Now further, people actually introduce R larger than 1 over GM2. And in this case, S is going to be negative. See, in a complex plane, remember earlier, our SWZ is here. Now by choosing R, this is original. Our pole, our 0 moves to new here. It's right on the right plane. And this will help eliminate that 90-degree phase shift. And it really helps the circuit to be more stable. So now let's look at a little bit further, one more concept before we conclude the lecture today. It's called a slew rate. Slew rate means rising rate. Now, because we know that any thing in a circuit, in electric circuits, you know that the current and voltage can hardly change instantaneously because the capacitance and inductance in the circuit. When you have a capacitor in the circuit, the voltage has to rise slowly. So in a slew rate definition is that if you have an amplifier with a gain over here, and you have an input, of a step input. You have a step function input. Ideally, if your gain is S infinity, you would get output to jump from 0 to maximum right away. So like in this case, this really like a follower, okay, input follower, which means if the gain is infinity, your output exactly is Vt. But in reality, A is not infinity. So which means the VO has to rise slowly. So VO is not gonna, so which means if you have an input of a step function over here, that's your is your input, your output will rise and eventually follow this. So the time it takes, rising time, TR, is really the slope, the rising rate, and it's typically called the slew rate. Okay? And because if you look at the circuit over here, in the second stage, we said that it looked like an integrator. So which means VO is not going to be rising instantaneously, but it's going to be like integration of the input. So if you have an input coming in, which here is coming for GM2, remember this in the previous slide, it becomes GM2 times VID, which is this I current coming in. So our VO is going to rise slowly, and how slow is you can write the time domain, or you can write in the frequency domain equation. You write the frequency domain that VO equal to this I divided by SCC is the rising rate. So S apparently we can transfer it into the frequency domain, but in the time domain we can also write down like this. We know that we again if we know I equal to C dV over dt, this is the equation that we learned from circuits, right? So for inductor, we know that V equal to L di dt. This is the kind of equation we already learned. So in this circuit, V across C is V equal to VO minus 0, right? So which is equal to VO. So we have I equal to C dVO over dt. And further, we can integrate on both sides. So we have VO equal to C I over C, and is integration over dt. Let me rewrite this in a better way. So we have dVO equal to I over C over dt. So we have VO equal to I over C. If I and C, so if I equal constant, now if I is not constant, the equation does not apply. So if I is constant, the integration basically over T. We can write this one over T over C, or I over C. No, we don't have to rewrite. So basically, we can write this into like a slow, we call it a slew rate times T. So this measures how fast your voltage rises at the output. So the faster the slew rate, the better for the circuit. But of course, the more expensive to design. And then you can see here, the slew rate definition has been defined as I over C. So the I equal to GM2 over times VID divided by C, right? So there's apparently the rate it goes up will be related to the CC. So the slew rate is apparently related to CC and GM2. So a smaller CC will result in large SR. A large, which is apparently the larger the slew rate, the better. So a large GM2 will also result in a larger slew rate, right? So that's what we really get from the slew rate definition. But if we plug in the I, because I is the, if you look at the DC operation instead of AC, so the I in the circuit can be defined as the gain of, so basically we can say here. So we can say GM1 equal to GM1, that's definition, equal to I over V1. So that's by definition, which means we can plug in this number to SR, which was equal to I over CC. Now from here, we get I equal to GM1 times VOV1, right? So now we plug in this one, we get GM1 over GM1 over VOV1, which is I, and then I equal GM1 times VOV1, okay, times VOV1, and divided by CC. And also from the previous equation, we could replace CC. That was in the definition of the unit gain. I think we got the unit gain to be, the unit gain was which equal to GM1 times WT. This is from what we get is the unit gain, the frequency was equal to CC over GM1. So this is what we get. So we're plugging this CC into this equation here. We get SR equal to omega T times VOV1. So basically, what we are saying is that a higher unit gain frequency and a higher VOV1 will increase the slew rate. Yeah. So this is really what we get for the amplifier. So by this time, I think we pretty much finished the lecture, and I think if we I want to maybe add here. What I want to do is to really just looking at what we have done for the two-stage amplifier, and we derived the middle band gain, and we derived the input resistance, we derived the output resistance, we designed the VCM range, we derived the VO range, we derived the transfer function for high frequency, and we found from here we found WP1, WP2, and WZ, and also we derived the unit gain factor of WT, and then from there we had this body plot, and then we also had this phase margin that was defined, phase, and also the gain margin for stability analysis, and then we added R to CC to improve the overall stability of the circuit, and finally we derived the slew rate of the amplifier. And we also mentioned that this circuit does not have output stage, which we can always add. And also we did not discuss feedback. Now, even though that CC and all CC plus R in the circuit, but it's not a true feedback. If you have to introduce a feedback, and this circuit will become a little different. So, however, in the circuit, you can always try to add a feedback and look at how this circuit would work. Remember, eventually this circuit becomes very simple, a two-stage circuit with a C and all C plus R in between, the output and the output of stage 1 and output of stage 2, right? But ultimately, this circuit eventually will become just a gain like this, and you have an input. And then you can always introduce additional feedback. And then you have your input come in, and you have a feedback. And this circuit will become more of a complete circuit. And this A becomes, in the circuit we calculate, it can be between 100 to 10,000 becomes based on the circuit parameters. In this chapter later on, we're not going to go deep in the next one, but basically you can have this whole thing replaced by this, you can have this whole circuit replaced by BJTs, and will become a BJT-based op-amp. And you can also add more stages, become like 3-stage amplifier, or even 4-stage. Remember in chapter 9, we introduced a multi-stage amplifier that with BJT, it has 4 stages. So this is where you really can find, how to design op-amp and how to design amplifier and how to connect everything together. Again, this kind of new material we're going to provide for you, and it's also going to be end the lecture. But just a reminder that on Monday, we're going to do a thorough review, and we're going to connect all the dots of the whole class from beginning to end. And also we're going to have a quiz, and then Wednesday we're going to have office hours. With that, I'm going to conclude the lecture. Unless you have any questions, if you have any questions, let me know, and you can either ask, unmute yourself, or you can send via chat, and I'll be glad to answer your questions. I'll stay here for a few more minutes before we end the class. I will upload the lecture slides and also the video. If you want to review the lecture and the slides and the video, you should be able to do that. And the video should be available in a few hours. Okay, let me see if I have any questions from my students. Who can see your message? Well, basically, if you send to the group, everybody can see the message. But if you send it to me, only I can see the message. You can send message to everyone, or you can send me message to me only. Okay. Okay. And slides.